Hello everyone, this is Samir from Audio Science Review. I have another tutorial for you on how to understand the measurements that we have on ASR forum. And by popular demand, this is about speakers. It's probably the most important tutorial of this series. Nothing determines the enjoyment and tonality and experience and fidelity that you get out of your audio system more than speakers do. And for those of you listening to headphones, is equivalent, although I'll do a different tutorial for that. The other measurements, measurement types, I could just jump into them and explain what the measurements are. But when it comes to speakers, we have to step back and understand a little bit of the basics of what we're looking for in speakers. The popular understanding is that everyone's different and everybody has a different taste in speakers, and that's why there are thousands of models of speakers out there. But research that started about 40, 50 years ago by Dr. Floyd Toole when he was at the Canadian Research Institute showed that listeners actually prefer speakers that have neutral sound. If a speaker had too much bass or too much treble, too much mid-range, those were less preferred to speakers that had basically a balanced response. That research was repeated, refined many times with more and more advanced setups and tools, and has been proven world over. There are a ton of companies that follow this research, even if they don't explicitly acknowledge it. And so it's important to understand that and buy into that. Even if you don't buy into it, the measurements can still be useful for you, but I highly suggest that you buy into that. So what does that mean to have a neutral speaker? Speaker has two sounds. One is what we call direct or on-axis sound. So I've got a speaker in here. If I point it at my ear, the first arrival of sound lands on my ear is what is the shortest path, which is direct line to the speaker. Again, we call that on-axis response. And for speaker to sound neutral, that on-axis response needs to be flat, ruler flat. Now, when we say flat, we don't mean flat when you measure it in your room. We mean when it's measured in an anechoic chamber with no reflections in the room at all. And there we want to get a flat line. Anything that's tilted up and down or goes up and comes down, all of that adds coloration. How does it add coloration? Well, if you have 5 dB more in bass, then it becomes bass heavy. If you have 5 dB too much at, say, 3 kilohertz, 4 kilohertz, it may sound bright. So the goal there is simple. You want it to have flat on axis, just like what we aspire to have in our electronics. When I measure an amplifier, we want to have a flat response. Same with speakers. It's not easily done like it's done in electronics, but it has to be done for us to have, neutral experience. But the speaker doesn't just generate one sound that hits our ear, and we don't listen in an anechoic chamber. When we listen in our room, the direct sound comes and arrives at our ear first, but then the sound from the speaker hits all the surfaces in the room and reflects, and then eventually winds up at our ear again. And there are countless reflections, right? From this speaker, it can hit the ceiling, it can hit the floor, it can hit the sidewalls. All of these can combine and arrive at our ear. Research shows that those reflections need to have similar tonality to the on-axis sound for us to hear a neutral sound. So if the on-axis, let's say, is ruler flat, but that other sound, the combined energy of all those that we call off-axis, is got a dip in it, let's say at 2 to 3 kilohertz, as many speakers do, then that's deficient in that. And what the brain more or less perceives is a sum of those two and does not perceive that speaker to be neutral. Now, I want to emphasize that the on-axis response is more important than the off-axis response in that, to a psychoacoustics principle called the precedence effect, the brain puts a lot more importance on the first arrival, the first sound that hits our ear, and tends to reduce the impact of off-axis response. But nevertheless, if the off-axis response is not good, then the preference for the speaker goes down just as well. All right, so how do we get on-axis response and how do we design speakers in general? As you see, and you probably know, is that speakers tend to have multiple drivers in them. Sometimes they may be one driver, but it may have multiple elements in them. Very few drivers are just single driver that do everything. Why? Because the requirements across audible range varies. At 20 hertz, we need to move a lot of air at very high amplitude for us to even hear a bass that low. Whereas at high frequencies, at 20 kilohertz, we don't need to move much air at all, and we don't need to be playing very loud, or we go deaf. So to solve that problem, from beginning of time, the speaker designers have resorted in using multiple drivers. If you use two of them, it's a two-way speakers. Use three of them, three-way, and four-way. I don't know if I've seen more than four-way speakers, but a sweet spot seems to be two-way or three-way speakers. There are such things as 2.5-way and so forth. I'm not going to get into that right now. So, and as you can see as examples of these two speakers behind me, the bigger that you make the woofer, the more power handling it tends to have, and the lower it can go, assuming you put in the right enclosure and so forth. You don't need to become a speaker designer at all to understand the concepts I'm talking about, but at high level, you got to have some appreciation that we have multiple drivers. Now, the way for this to work, we need to split the incoming signal and feed the right signal to the woofer, which is the larger one, and the high frequencies, we got to feed it to the tweeter that's above, and if we have a mid-range, we got to split that yet again. And that's done through a circuit called a crossover. And crossover's job is just basically filters, either low pass or high pass or band pass. And it chops off the audio range more or less. It doesn't do it absolutely. There's a slope to it, and feeds the area that needs to go to every driver. Now, with careful design, you can make the two drivers blend. So I can roll off the bass as it goes to the woofer, and then I can let the highs gradually come up so that when the two combine, I can get a flat on-axis response from the combination, as if I have a single driver rather than multiple drivers. Not necessarily trivial to do, but there are computer tools you can use and optimization and so forth, and it can be done within the confines of what we can measure. So that gives you a flat on-axis response, but it does not give you a flat off-axis response. Remember, off-axis is what goes sideways and hits the wall and so forth. Why doesn't it do that? Why doesn't the sound coming out of a driver be the same as direct versus what goes off the sides? It sounds like it should be all the same, but that's not the case. We have a problem in audio in that the bandwidth that we were trying to cover in audio goes from 20 hertz to 20 kilohertz. That's a very large ratio for acoustic product. For electronics, it's a walk in the park. It's not much, but for acoustic product, that's a wide range. And it causes a specific problem, which we call directivity with speakers, in that there's a concept which is a wavelength. If you have a sine wave, sort of goes up and comes down. If you measure the distance between those two endpoints, there's actually a distance to it, and you can express that in feet or meters, called a wavelength. And it's just a simple formula which is inversely proportional to the frequency. The higher the frequency, the smaller the wavelength, and the lower the frequency, the larger the wavelength. So there are online calculators. You don't have to do the math, although math is pretty straightforward. And here I've put in 20 hertz, and you can see that at 20 hertz, the wavelength is 17 meters, and convert that to feet for those of you who live in the US and deal with imperial metrics, is 56 feet. So at 20 hertz, a single sine wave coming out of the speaker, assuming these things could produce 20 hertz, is quite long. Whereas if I go now to 20,000 hertz, which is at 20 kilohertz, and look at what happens now, it's only 0.05 feet. So we went from 57 feet to 1/20th of a feet. So now we're talking a couple of inches, and we can convert that to centimeters. It's only 1.7 centimeters. So the wavelength at 20 kilohertz is tiny, and the wavelength at 20 hertz is massive. It's bigger than most rooms. So, well, what do I need to know that? There's a concept of physics here that you cannot get around. It's a fundamental law of physics that has to do with transducer that says, if the wavelength of a sound that you're trying to produce, whatever length that is, and you compare it to the diameter of the driver that's trying to produce it, if the wavelength is much larger than the wavelength of the driver, the sound comes out omnidirectional. For that reason, if you look at the directivity, as we call it, how sound spreads, 20 hertz coming out of a speaker will go all the way around the speaker. You can go behind the speaker and hear the same bass as you would in front of the speaker at 20 hertz, 30 hertz, 40 hertz, 50 hertz, because the wavelength, again, is 50, 60, 70 feet. And, the driver here is, it's not even 1 foot in this case. And even the larger drivers, maybe it's just 1 foot, whereas the wavelength is 50 foot. So it's much, much wider than that. Now, conversely, when the wavelength of the sound gets smaller than the size of the driver does what we call beaming. It narrows its focus like a flashlight that's zooming in, and the sound that it radiates becomes narrower and narrower and narrower. It can get extremely narrow depending on how bad that ratio is. So if I didn't have this tweeter and I just played everything out of one woofer, initially everything comes out omnidirectional out of that driver. But as the wavelength starts to get close to the dimensions of this woofer, which happens around 1 or 2 kilohertz, let's say, the sound starts to narrow down. And again, it'll keep narrowing until it becomes like a laser-focused sound that comes out of that single driver. Now, we have a problem in that remember what I said about how we build the speaker is that we give part of the sound to the woofer, and this large woofer, and at some point we hand off the signal to the little tweeter. Look at this guy with an 8-inch woofer and a 1-inch or 1 1/4-inch tweeter. At the time that we start to hand the sound from the woofer to the tweeter, this woofer would have started to narrow its beam width, is starting to beam. Not all the way to nothing, because we're still, let's say, crossover is only 1 kilohertz. It's not 20 kilohertz. So when we hand that 1 kilohertz sound wave duty from this woofer, and we just hand it to this little guy, the tweeter, at that moment the equation inverses, because the wavelength is considerably larger relative to the size of this tweeter, whereas in here may have been equal or smaller than the size of this woofer. So what does that mean? On-axis sounds does not change. Nothing about this. The direct sound, remember, whether sound is beaming or not beaming, what comes out in the middle is the same. But what happens is that the sound that used to be narrowing in the woofer gets handed to the tweeter, and the tweeter all of a sudden becomes omnidirectional, or relatively so, and it starts to send a lot more energy to the size than the woofer was. So what that means is that if I measure the sound from an angle, and I sweep this sound at 20 hertz, everything's omnidirectional, it's all good. But as I get to 1 kilohertz, where the crossover is, I notice a drop because this woofer is starting to narrow its beam, so the sound drops. But when I hand the sound to the tweeter, let's say by 3 kilohertz is fully taken over, all of a sudden it snaps wide again, because this guy is a tiny little driver, and we're talking 2 or 3 feet, let's say, of the wavelength, and that is more or less much wider. It's not omnidirectional, but let's say it jumps to 60, 70 degrees, which means that if you stand next to the speaker, you now have a hole in the response as it got narrower, and then all of a sudden became wider when it was handed to this guy. So the frequency response at an angle for the speaker is no longer the same as on-axis. On-axis was flat because we didn't have to worry about this directivity issue. We just had to worry about just what the on-axis response is. But off-axis, depending on where I am, what angle, and so forth, can be radically different. So how do we fix this? Well, the most common solution to it is what's called a waveguide, and you can see that shape in here. If you see this carved out shape, what this will do is that it'll take the beam width of the tweeter that's about to take over and be very wide, and it narrows it down. It focuses its energy so that the beam width, the directivity of this guy, matches directivity of this woofer. So in a way, we penalize this guy's ability to play very wide, although we help it by letting it focus its energy forward, and by doing that we're matching the directivity of these two drivers. Okay, so you're with me? If we match the directivity, means that the energy that goes to the side at an angle is the same whether I'm measuring the woofer versus what I'm measuring the tweeter, then the off-axis response is going to be similar to what the on-axis response is. Now, eventually, this tweeter will beam because it will also get to a point where the wavelengths are relatively small to that thing, and the highs start to collapse. That tends to be okay. We're not as worried about when that happens at 15 to 20 kilohertz. We do worry about it when it happens at 1 or 2 kilohertz, which is a very critical region for, in music, and, voices and lower treble and so forth. And so we don't want to see directivity error in mid-frequencies. But a gentle narrowing of overall response of a speaker is fine. So just netting all this out is that the design of this speaker, a good speaker that's neutral, requires on-axis that's basically ruler flat, an off-axis that blends these two and is similar, but it can actually have a tilt to it. So that means we could have less high frequencies when we are on the side, but we want it to be connected as smoothly as we can get. We don't want to have a dip in the off-axis or a peaking. We want it to have as smooth as we can get. And all of this actually, this is shown in my measurements and reviews, so you don't have to guess. But at high level, you can look at the speaker. If this waveguide wasn't there, you could go, there could be problems. Now, there are some solutions and workarounds that may not involve having as good of a waveguide, and their waveguides are better than others. But generally speaking, the current understanding for a good speaker is that somehow you got to mitigate the fact that the beam width of these two drivers will not match, and that you want to mitigate that. Now, by the way, this is a smaller brother of this guy. Its woofer is much smaller, and the woofer and tweeter are much closer in size, which means that this guy is not as hard to design its directivity because there is not that much difference between the two drivers. Whereas the larger the woofer gets, the bigger you have a ratio as far as woofer to tweeter, and the bigger problem you have on your hand. So, but you then get more bass and other capabilities, but know that, sticking a 15-inch woofer in here and a 1-inch tweeter, you're buying yourself a lot of grief as far as the off-axis response of this speaker is concerned. Okay, so again, I'll show you all this stuff in measurements, but I just want to make sure at high level you understand that our goal is that. Now, one consideration is that you can get a speaker that has great on-axis and poor off-axis, and it can't sound good. You say, well, you just got done telling me that the sound on the side that reflects is going to be bad because it won't match the on-axis. That's true, but depending on where you position the speaker in your room, what treatments you have, what absorbers you have, you can somewhat mitigate the fact that the off-axis response is poor. You'll be spending a lot more time mucking with the speaker in the room to try to get it to sound good. And indeed, there are speakers, people buy very expensive high-end speakers that have very poor directivity, and people spend forever trying to make them sound good in a room. And it can be done. You can mitigate it to some extent. But why do that? If you get a speaker that has great on-axis and smooth directivity, as we call it, then you can place it in almost any room, and the speaker will perform similarly. It doesn't have the ups and downs of, oh gosh, the speaker sounded good at a dealer, I took it home, sounded terrible. Or I said it sounded good, and you bought it, put it in your room, it sounded terrible. A speaker that has good directivity tends to be very, very friendly to your room. And the second thing, which I'll also emphasize when I get into showing you the actual measurement, is that you can equalize the response of a speaker that has good directivity, meaning again, on and off axis are similar. If they're similar, you can actually equalize it better. What is equalization? It means we boost and lower different frequencies upstream of the speaker. So if we do that, it impacts both direct response of a speaker and his off-axis response. So to the extent both of them are similar, but both of them are wrong, let's say there's a dip at 2 kilohertz, I can boost that, and both on and off-axis will obey and work together. If they're not in sync with each other, you can still equalize them, but again, it could be more tricky. You could equalize them and make things worse because you made the off-axis a lot worse, or you fixed the off-axis and the on-axis got a lot worse. So all else being equal, you want to have a speaker that's well designed. You want your designer to have done both of these things for you. Okay, this is the most key thing you want to know about speakers. So let's jump into a review, which happens to be this M-Audio speaker. It's called a BX8D3. Fortunately, it's discontinued more or less, but there's some amazing bargains out there. It's not a perfect speaker, but it's a speaker I like, and you'll see in a few seconds why I like it. But it's the one that's sitting over here, and that's the one that we're looking at. So we have the two-way configuration. I usually show the back panel in here. There's a port in here, and this port can cause problems sometimes. Remember I talked about the wavelength of sound? When the wavelength of sound starts to match, become a ratio of the height, width, or the depth of a speaker, you can get what's called resonances, in that it self-amplifies those frequencies and not others. And those resonances then come out of the port. When the port's in the back, it tends to be less audible because it's got to hit the wall and come at you. When the port's in the front, it can be worse. So as a general rule, I like the ports in the back better than I like the ports in the front. But we'll measure actually all of these effects, okay? So how do we assess the speaker's response then in all these dimensions that I talked about? If I just showed you on-axis response, then you wouldn't know the off-axis, right? You want to have a way to encapsulate all of that. Now, what off-axis response do I show you? What angles? Which one's important, which ones are not? We'll get to that in a second. So step one in measuring a speaker is that it has to be anechoic. What does that mean? So that means you got to measure a speaker in an anechoic chamber. A crappy anechoic chamber probably costs a few $100,000. A very good one probably costs $500,000 to $1 million. And the one that you want that's flat down to 20 hertz probably costs you a few $1 million and basically doesn't exist. So, but that's been the norm until about 8 to 10 years ago, was that if you wanted to get the anechoic response of a speaker, you put it in an anechoic chamber, it has these wedges that basically swallows the reflections, and you just then put microphones and you measure the on-axis response. There are also what I call DIY techniques for measuring speakers. Those let you measure the high frequencies fairly accurately using what's called a gated measurement. And then you got to do what's called the ground plane measurements, and you got to stitch those two together. If it's not done right, it can show you wrong results. So be very careful in interpreting those things. Many people, there are some sites that only show you response from a few hundred hertz and up. When they do that, know that that's not a good measurement, because it basically has no accuracy below a few hundred hertz. So all else being equal, you do want to have and basically an anechoic measurement that go down to as low frequency you want, or 20 hertz in this case. How do I measure things? Well, take advantage of advancement in signal processing using a system called Klippel near field scanning. Klippel is a company in Germany that's started by Dr. Klippel, and their focus is on measurements of loudspeakers and transducers. About 10 years ago, working with some research students, and they came up with a method called a near field scanner or near field measurements. So what they do is that you put the speaker in a room, and let me see if I can quickly bring it up as we are talking. Oops. Oops. Sorry, I didn't think about bringing this up earlier. So a near-field scanner is a robotic system that you put the speaker on a stand. Let me see if I can... Yeah, hopefully you can see in here. So you put the speaker on a stand, and this robotic arm with a single microphone around it will scan the speaker in 360 degrees and up and down. So he basically tries to get a cylinder, but for the purpose of this discussion, just assume it's a globe around the speaker. And he does this at very close distance. Now, normally that's not a proper way to measure a speaker, because if I put a microphone in here, depending on how high or how low I have it, I would pick up too much of the woofer or too much of the tweeter. So you usually want to measure a speaker at what is called a far field location. This, on purpose, violates that and actually sticks the microphone very close. Think about it like 1/3 to 1/2 a meter, 2 to 3 feet, and measures the this basically 1,000 points or more around in 3D space around this. Now, the advantage of measuring close is that all the ambient noise, let's say there's an air conditioner running or maybe there's somebody walking, those get lost in the noise literally because your microphone is very close to the speaker and you're picking up a very, very strong signal. So it allows you to measure a speaker in a non-quiet room. Anechoic chambers are usually built to not only be anechoic, not reflecting, but also be extremely quiet. With this system, you don't need to do that. The problem is that those measurements, as I just said, they're actually incorrect because you're measuring too close to the speaker and the two drivers haven't integrated. But through a pretty advanced computational phase in that you take these 1,000 measurements and you convert these single measurements into a complete computation of the sound field, which is if I had a formula that I could just plug in any angle, any distance, it would spit out exactly what the frequency response of the speaker is at any one point. It actually computes this model, and when I compute that model, I can put in 1 meter, 2 meters, 5 meters, 10 meters, and I can put any angle I want, and it will spit out the answer. So just think about it as solving an algebraic equation, except that instead of having, x plus y equals 12 and having 2 formulas, it has 1,000 formulas with 1,000 coefficients. So it's a large thing, and it takes about 20 to 30 minutes for this computational phase on a modern computer to run. But once it does that, you have the full sound field. So not only did you enjoy a much better signal noise ratio when you measured the speaker, you also managed to solve a problem of basically expressing the sound field at any point you want. Whereas in an anechoic chamber, if it's not too big and I put my microphone here, then I may not be in the correct far field, and certainly not where I would normally sit in a normal living room to listen to music. I would be much farther than 2 to 3 feet, but building large anechoic chambers is expensive, so we don't do that. So make a long story short, that's where this near field scanner part comes from. NFS for short. So Klippel is the name of the company. Don't be confused if somebody just says Klippel, doesn't mean this system is in use. Klippel has a base measurement system that can generate tones and measure it, but then you buy this extra NFS system and to complement that and to have this robotic system run. Typical time for scanning is about 2.5 to 3 hours in the number of points I use. Sometimes I use more. I don't usually use less. So about 2.5 to 3 hours is typical. I let it run, and I have to set it up. It takes about half hour to set it up, configure it, but then you let it run for 3 hours and spits out this raw, usually close to a gigabyte worth of data, and you take that measurement data, then post-process for a half hour, and out pops out basically the measurements that I'm going to explain to you down here. But there's a second part to this. Remember I said anechoic room. I don't have an anechoic chamber. I don't have $1 million to spend on this, and nor would I have the room even if I had the money to spend on it. There's another clever thing computationally you could do, which is you can measure the sound field at one point. You can also measure it at the second point. And knowing that distance, you can actually figure out what is an oncoming sound wave to you versus sound that has gone and taken a longer path from reflecting off a wall and coming back. And you can then eliminate and filter out those reflections. And this is called the field separation. And it's an optional part of this system. It's just software, but it's optional. If you have that software, it's able to then generate truly anechoic chamber. It literally takes all the reflections in the room and he subtracts them out. So we subtracted out the noise that's in the room, we subtracted the reflections. Now what that means is that I can take a speaker and I can measure it anywhere. Indeed, I have this system placed in my very large 3-car garage, a domestic US garage with 12 to 14 foot ceilings, which helps to have larger space, but some of the measurements I'll talk about in a second. But you just set the speaker in and I can measure speakers up to about 6 foot high Above that, it can be tough. But that covers just about every speaker that we're interested in measuring. You do have to lift the speaker up to this 5-foot pedestal, and I have extensions that let me enlarge that pedestal. So non-trivial if you have a 120 pound or 200 pound speaker you're trying to place on this. They have accommodation for having a crane. You can actually lift the speaker and hang it on top of this. But anyway, I have this system. Unfortunately, the system is not cheap. It's about $110,000 for this system. You got to buy it from Germany, pay in euros, and deal with importing and so forth. So it's not something you can snap your fingers and get it. But it is essential because it will give us anechoic data, which is what all the research is based on. Okay? So we take this data and then we express it in multiple ways. First thing we do is that we show it in what is called the on-axis response, which is the black line. So first thing I do when you look at this graph that I post, you look at this line in here and see how flat it is. And we see that in bass frequencies it's pretty flat. When it comes to speakers, we don't worry about little variations like this. It's flat, then all of a sudden some strange happens. There's a peaking over here, then it goes down, and then all of a sudden it dips again for a while, and it comes back up, and it dips again, and dips again, and dips again. And we clearly don't want to see all these variations, but they're there, and I'll address them when I talk about the equalization and listening test. Now, what is this peaking in here? Why is there peaking? To understand that, you want to look at these two other graphs. The one in blue, dash blue in here, is early reflections. When I said reflections matter, some reflections are a lot louder than others. The sound that hits the sidewall and comes to my ear is much stronger than the sound that goes all the way behind me, hits the back wall, then comes to me. It's traveling longer distance, and the sound drops by a factor of, with the power of 2, so it drops off massively. So research has shown that there are X number of reflections that are the strongest in most typical rooms. So if we take all of those and weigh them properly, meaning some are more important than others, and combine them all together, you get what is called this early reflections. And we plot that in here as a measure of frequency response of the off-axis. So instead of looking at 15 different off-axis response, we'll look at the sum of them in expressing these early reflections. And then if we take the energy that comes out of the speaker in full 360 degrees and sum all that, you get this red graph. This used to be something people went by, but it turns out to not be correct. You do not want to use the sound power of the entire speaker. It's called the sound power, because if you did that, you're putting equal value on every sound waves coming out of the speaker, and that's not correct. Sound that's, let's say again, goes at some screwy angle and reflects 3 times before it arrives at my ear, that's not as important as sound that just instantly hits the floor, let's say, and come to my ear. Okay, but it's there and we show it. In bass frequencies tends to be the thing that we care about because everything's omnidirectional. So the reason I just explained all this stuff is that what I do is that first I look at it on axis. If it's flat, we're done. We move on to something else. But if it's not flat, I then look at these other ones and see if they mimic what the on-axis response is doing. When they all mimic each other, it means that that anomaly isn't just directly on axis, but it also occurs in all different directions. When that's the case, we call this a resonance. I explained earlier what a resonance was. Resonance is when you give X amount of energy to the speaker and it plays back X plus Y. Sort of like a tuning fork or a swing. If you just get it the right oscillation, you don't need as much energy to get it to do that. So in a way, the speaker becomes more efficient and spits out more energy than we want. And when that happens, and it also shows up in off-axis, we call this a resonance. And you can see, I've noted that it's a resonance at 590 hertz, so that's exactly what that is. We don't know what's caused it, but we can see that it's there. And good news is that equalization is extremely effective on this thing. So I can take an EQ and I can dial a filter that has this similar kind of shape. I can pull that down as if nothing's happened. And I actually gain something in that since the speaker is more efficient there, when I lower that value, it's actually trying less hard and it'll actually generate less distortion. So not only do I get better tonality when I fix that with equalization, I actually get lower distortion. And so that's a good thing and we can fix it. Likewise, we can see also in here that when there's a dip in here, we also see there's a dip in these things too. So it's a general characteristics of this speaker. Okay, now down here we see this blue and this orange curve. So these two are really just a difference between these two graphs and the on-axis. So we want to see how different the off-axis response is versus the on-axis, and then the sound power. So just two different ones. What does that mean in plain English is that ideally we want to see a line that has whatever slope. The slope is less critical, but we want it to be as smooth as we can get it. And you can see this is actually pretty smooth. You know, there's a little bit of error. Remember I said when we're handing woofer to the tweeter, there can be some error. We can see both of these guys sort of, they're going up like this. That means the beam is gradually narrowing. That's fine. But then as soon as the tweeter takes over, it sort of snaps a little wider. But then it still continues. So bad speakers will have really sudden jumps in here, far worse than what you're seeing over here. Okay, but this is less important. The number one thing you look at in here, in an instant, your eye should go to the black line and say, what is the black line doing? Is it like this line that I've drawn myself manually, this red one? And is it not? And we see that it's pretty good in here. We have some anomalies here and there. How bad they are, we have to judge that. Okay, now I do another test which has actually nothing to do with that, and it's not anechoic, in that to troubleshoot where this peaking coming from. I mean, we've got all of these components. We have a port in the back, we have woofers, we have all this stuff. There could be a lot of things that could be causing this problem. What I use that I take the near field scanner and I take his microphone and I stick it very close to each driver. So I get it right in front of the woofer, then I get it right in front of the tweeter, and I also get it right in front of the port in the back. And I plot those responses. So here we're looking here and we see this is the port. The port is designed to extend low frequencies, and we see that it's doing that. It goes lower than the woofer. It goes down here. And then we see some resonances from the enclosure coming out. And what are the resonances? Every time you see a peak in here. In badly done speakers, these resonances actually shoot up to become very close or even higher than the response of the woofer itself. When they do that, they screw up the on-axis response in here, and we will know right away it's because the cabinet is what's contributing to it. So you may be able to put some stuffing in there and reduce those, and you can curse the designers for skimping over, you know, managing that. And there are more advanced techniques to get rid of those reflections. They're non-trivial sometimes to get rid of on this thing. But in this case, it just happens to actually work out reasonably well. But when I did the same measurement, just measuring the woofer itself, I noticed that wiggles actually in the woofer. This is almost the first time I've seen this. Almost always that kind of jump like this is from the port. But in this case, it's not, which means that somehow this woofer combined with its cabinet enclosure, maybe it's loose, maybe something's going on there where it literally started to resonate with the enclosure or something. So I called it woofer resonance, but it really should say woofer cause resonance. And then I do the same thing by sticking the microphone directly in front of the tweeter, and we see the tweeter response, and we see that it's uneven on its own. That means that stuff wasn't caused by the woofer. This is woofer dropping like a rock because of its crossover, and the tweeter is what's generating this problem right here. So if we go back up here, now we know the cause of both of these. We see this. This basically says the tweeter they picked doesn't have a flat response. This is an active speaker, I believe. And there's really no excuse in an active speaker to not correct for this, because they could have put filters in there if they had the signal processing power to flatten this, and they didn't. This actually sells now discounted for like $120, $150 each, which is remarkable, so I wouldn't fault it here. But for a great speaker, we would have wanted to have a driver that's smooth, and if it's not, then have correction for it in the DSP inside this. Now, I talked about the off-axis response and how we take a bunch of them and combine them together to generate that early reflections, but we can actually tease those apart and look at each one of them, and you can see them all in here plotted on top of each other, and the floor bounce, ceiling bounce, the front wall, by the way, is the wall that's from the front of the speaker. So what the speaker sees is his front wall. And we have the side walls, and we have rear wall, what is behind the thing. And then in green is all of them combined, which is what we saw in the other graph. And I just put a trend line in here. These lines I just draw it by ear. It's not by eye. It's not mathematically accurate. But anyway, it sort of shows you a slope. And again, there's nothing wrong with having a slope that overall goes down. But I draw the line to see that things are sticking up above it and things are sticking below it. We can see that, we don't have an ideal response. We have our bump in here, and we have our, dip over here, and we have the variation in Twitter. Now, one thing this graph lets you do is decide where you need to put absorbers and or other mitigations. For example, if you look in here, I've got a ceiling reflections in dashed red. And we have a dip in here already. By allowing the ceiling reflections to go on, they make this dip worse. That if we didn't have ceiling reflections, this dip would be less pronounced and it would go up higher. So what does that mean? You could put an absorber on the ceiling and it's needed from 1,000 hertz and higher. That means it doesn't have to be very thick. A couple of inches is probably fine. But if that's not doable, make sure the ceiling is tall. So if you have a tall ceiling like I do in my listening space, that helps. Likewise, floor bounce, we can look at it and see, is floor bounce making things worse? Yeah, it is making things worse. It's this blue line. We can see it's making this peak worse and it's making this dip worse. So putting a carpet in front is useful. Unfortunately, this gets used for, this specific speaker gets used in near field as a monitoring thing, so it's probably going to bounce off the console in front of you. And that's just life. These two-way speakers vertically never have very good response. But now you know something about what you can do as far as treatments on this thing. Okay? There's a clever scheme that says, look, all of this is fine and dandy, but how is it going to sound in my room? That what I hear in my room is a sum of the on-axis and off-axis. Can we blend those two together and make a prediction? Or estimation in this case. And we can, and based on some research and verification of, comparison to the real room, in that if we combine all that based on a specific formula, we get this kind of response. And you should see basically that it makes sense in that we still have the little, notch in here, and we still have this dip that we talked about, and we see that this overall sound slopes down. Why is this slope down? On axis was more or less flat, but off axis was like this. So we combine the two, we average them out, it winds up pointing down. The flatter this curve is, the more bright the speaker is. The more it dips, the less bright it is. That means more of the highs are attenuated, they're reflecting off the sidewalls. So in general, you want to have, for domestic use, so domestic means enjoyment of music, you tend to want to have this sloping down. For professional use, mixing and mastering music, you may want to have this flatter, and the more professional speakers tend to be flatter. I tend to find both of them just fine, and at any rate, you need to apply equalization anyway to give it the sound tonality that you want. So I don't care what the slope is, but just know that generally for your room, the sum you want to be poking down. And we can look at this thing again. I draw a trend line saying, look, we got two problem areas in here, but the rest of it actually looks pretty good. Look at how good it's matching my line. Look at how good it's matching my line. One thing I didn't talk about is the bass extension. This speaker, this is 20, 30, 40 hertz, 50 hertz. Well, we're barely down at 50 hertz, then this thing goes all the way down to some 30 hertz, despite being a little speaker and quite cheap. Well, it's not very little, but for in grand scheme of things, it's somewhat little. The larger one is what we're looking at. But it has extremely good bass extension, and that's one of the things I found impressive. Okay, so all of this is standardized in a standard called the CEA or CTA 2034, and you must, by standard, show the measurements like this. This first one over here, this is made up measurement by me, but other people do the same thing. But this one's part of the standard, these early reflections, and estimated in-room reflection. One key thing about this, you will never, ever measure this response in your room, because as soon as you put the speaker in a room, the bass frequencies actually get modulated by your room, and you wind up with very large variations in here. So this is assuming an idealized room that's been fully equalized or has tons and tons of treatment in it to have no modal response, as we call it, in bass frequency. frequencies. So don't be confused about that. You could take the speakers and put it in a room, and it may sound way too boomy. And it doesn't sound boomy because it has too much bass. It has boomy because your room has certain room modes that has added 10, 15, 20 dB at certain frequencies to the bass region. So here we're trying to judge the speaker. We're not trying to judge a room. So this is a room-independent prediction, not room-dependent. And the more bass the speaker produces, the more it excites those room modes. So be careful when you listen to this speakers in different rooms. The bass dominates as far as the room is concerned, room impact, and so you don't get the same sound with bass. Higher frequencies, speaker dominates. All right, so that was our tonality testing. We then get into a little bit of a less charted territory, which is, okay, that's our, how balanced the speaker is, but what if I crank it up? Is it going to get distorted? Is it going to bottom out? Is it going to rattle? Is it going to scratch? Or is it just going to play as loud as I want to play? So a long time ago, I started this process of measuring both the frequency response, but also importantly, the distortion characteristics of the speaker at 2 levels, and 86 dB and 96 dB SPL at 1 meter, or 3.3 feet. Okay, and where did I get these from? There's another site called Soundstage that was measuring things, I think only at 96, I don't remember, or 86, I forget, I think it was 86. And so I started with 86, and then I was like, well, is there a trend? Why don't we go 10 dB higher? And I measured at 10 dB, 96 dB. I would say about 90% of the speakers that I measure have no trouble reaching these, even small speakers, even that little guy. I think that one maybe stopped at 90, but almost always every speaker I measure, it goes up to 96 dB unless it's trivially small, tiny speaker. So in my book, it better play 96 dB at 1 meter. You may say, well, that's quite loud. It is not quite loud in bass where most of the energy in your music is. 96 dB is only 20, 30 dB above threshold of hearing. So you do want it to be quite loud. But yes, at high frequencies, it's deafening. I wear hearing protection when I measure these. Okay, I use the Klippel setup to make this measurement because it gives the robotic arm lets me position the microphone extremely precisely, but I don't try to generate anechoic response. It's not necessary in my large space that I use, and I always use the same space on this thing. So how do you read this graph? This is the frequency response, in-room frequency response this time in my room, my garage, but you can actually see the same signatures. We see the same peaking in here and the same valley in here. So this proves that the anechoic measurements are representing actual performance of the speaker in room. But now you see some peaking in here because there are reflections in where I measure the speaker. And I've drawn an arbitrary line of 50 dB in here. Where did I get that? I just decided to pick that as a reference. Everything needs to have a reference, so you know if some too high, too bad, or too low. So here we go ahead and look at this at 86 dB and say, what is our responses for total distortion? And the total distortion is this red line in here. And we see that essentially it only comes up above my 50 dB response, just in the lowest of bass frequencies. And then from then on is well below the line. And where our hearing is most sensitive is this region. And in this region, it's extremely low distortion. I mean, we're talking below, 20 dB SPL. So it's extremely low distortion in this region, which is quite good. Now, naturally, when I boost the input by 10 dB or the playback level by 10 dB, now the woofer starts to get pushed a lot harder and starts to distort. Whenever you take a driver and push it out of its center position, the farther it goes out of its center position, the more distortion generates. Fortunately, our hearing is not super sensitive to distortion here. So this is actually not too bad. There are speakers where this actually will cross the actual response of the speaker, which means it has 100% total harmonic distortion. Now, sometimes this graph is informative, sometimes this one is. This is the identical measurement, same measurement, just expressed as a different set of numbers. Here we see the absolute amount of distortion, but if the response is going down and this is also going down, we care about the ratio of these two. So put another way, we care about how much distortion we have relative to our signal. So because our frequency response is not flat, it is useful most of the time to look at this as a ratio. How much distortion do we have relative to our signal? And here we see that we have a peak in distortion, 4.5%. It sounds like a lot, but again, remember these low frequency harmonics fall below a threshold of hearing. So, and you can see how beautiful this is in higher frequencies, but it's just hugging this 0% line in here. When we go to 96 dB, still extremely acceptable for what is basically a budget speaker in a small enclosure. Yes, it starts to complain, and we see that there, by the way, whenever there are these narrow spikes, that means there are also resonances in here that are causing problems. So, and this is going off the chart in here. But turns out this is still subjectively good because the response in here is so clean. You with me? All right, we'll revisit this later on when it comes to listening tests. Now we go back to our friend. I talked about the Beamwidth and directivity. We can actually plot that, which is we measure at what point we have 6 dB of drop-off. So just, if you don't know what dB is, don't worry about it. Just assume that we pick a constant level of less energy than on axis. What would that line look like? And we pick 6 dB, it becomes this red line, and that's what I use. And ideally, we want to see a flat line in here. At low frequencies, everything's omnidirectional, so life is good. But when it narrows, remember, we don't want to have variations between when the woofer is playing, which is this region, to what the tweeter is playing, which is this region. We want to have these two blend well. And look at how well these two blend in here. They blend quite good in here. We have a little bit of peaking in here and a little bit of narrowing. That's fine. Now, one thing I measure also is how many degrees is that flatness being maintained, and is basically plus 60 degrees and minus 60 degrees. This isn't horizontal dimension, by the way. So horizontally, up to 60 degrees on either side, or 120 degrees total, the tonality is actually quite similar to on axis. This is very good for far field, and even for near field, where you're sitting in a chair and going left and right, or you have a client sitting next to you and they've got to hear the same thing, but they're offset than you. This is very good. 60 degrees tends to be the average. There are speakers that are 50 or even lower, and some that they go higher. But by far, the most common is 60 degrees, and that's good in my book. Instead of showing it as line, we can show basically a heat map, and you can see in here the same kind of thing, but the visualization is prettier, and maybe you can get more insight in here. But you can see the effect in here very nicely, that we have basically what's called controlled directivity if this thing extended all the way to the end that way. So we have, omnidirectional in here, plus or minus 180 degrees, and then we narrow down, and then we maintain that narrowness till we can't, and then we start and keep getting narrower. And again, as I explained, anything above 10 kilohertz is fine. Vertically is a different story. So we're measuring, right now we went left and right, and now we also want to go up and down. We have a problem in that as we move from here, the distance from my finger and the two drivers changes. And there comes a point where there's a difference, enough of a difference between the two, in that the one waveform actually twists 180 degrees and starts to cancel the other one. So you actually get a dip there. If you listen to the speaker and you say, oh, sounds great, as you go higher and higher, you get to a point where all of a sudden you lose a chunk of your frequency response. Then if you go above that, things get better. And we can see that in here in what I call the two eyes. So 0 is our on-axis response, is this line in the middle. And as soon as we go 20, 30 degrees above it, we all of a sudden hit this eye. This eye means energy is substantially reduced, so we're no longer red, we're much lower SPL, and that means we have a hole. And then likewise, if we go down below the speaker by the same number of degrees, you wind up losing that. So almost in 99% of the case, unless you have a coaxial speaker, doesn't have this issue because both of them are in the same position. Non-coaxial drivers, two-way systems will have this problem, and what it means is that you better listen at on axis or just slightly off axis. So like this speaker right now is 4 or 5 inches below my ear. You should position it where you tilt it back so that you're listening on axis. A lot of times you see this comment in here, stay at tweeter axis. Don't go way above, way below, because you just screwed up your on-axis response, because remember, this is the response at this angle. So if I go up 30 degrees, I'm hearing a frequency response with a hole in it at 3 kilohertz. Not a good thing. So almost always, unless said otherwise, speakers should be pointed at your ears with that. Forgot to mention that every review that I do, there's a notation in there that tells you where the reference axis is. So some companies document this, some of them don't, but almost 90% of the time, unless said otherwise, I measure relative to the tweeter being referenced. Sometimes I go down a little bit below, I do some experimentation, but when we say tweeter axis, it means reference axis, usually means the tweeter, but sometimes maybe 1 or 2 inches below. If you sit far, it doesn't make any difference. If you sit very close, that little bit could make a difference. So more or less point the tweeter at your face and you're golden. Okay, so vertically, we're not maintaining that. Now, it turns out perceptually, we're not as sensitive to these responsors, because indeed, that sound wave that's going up 30 degrees has got this hole in it and is hitting the ceiling coming down. Isn't that a bad thing? Turns out perceptually, we're not as sensitive to vertical reflections having poor tonality versus the horizontal response. So it's not as bad there. So this is forgiven, although in a perfect world, you would have both of them look like this, okay? Basically, we're done by this point. I have 2 more measurements because people ask for them, but they have almost no value. One is called this CST or Waterfall, and basically says, give me the frequency response, but give it to me over time. And the idea is that, okay, if you look at the slice in time, if something elongates, means that it's hanging in the breeze, which means there's a resonance there or some other stored energy that people call. Turns out this thing, everything that's in here is actually originally in here in the frequency response as well. More or less, some exceptions, but I won't. But look at this thing, for example, in here. We said this was a resonance, right? Around 590 hertz. So we go down here. What do we find at 590 hertz? That same frequency response peak, but look at this. That giant hanging in the breeze, you know, in space is shown in here too. It looks pretty, it looks fancy, but we saw that already. But notice over here, for example, there's not any resolution in here. There are about half a dozen parameters that determine how this graph looks. I can make this graph look as ugly as you want, as pretty as you want. And it requires is an art in knowing what the parameters should be set to. If you're designing a speaker or doing some research, you can use the waterfall displays, tune them correctly to the problem you're looking for. As a general graph, it has essentially no value, but you know, it shows you some of these resonances that are there, and if you want to glance at them. But usually, whenever there's a peak in the frequency response, there's a corresponding resonance in here that drags on, and I know them to make people happy. This one's really useless in my opinion, but people keep asking for this step response. Stereophile shows this thing, and basically, you know, it simulates computationally. It doesn't actually measure this directly, but computation gives you this step response, which says, if I go from nothing to a signal and stay there, what would the speaker produce? And usually that edge is high frequency, so the tweeter response is the first thing you see, and then the woofer takes its time and shows this thing. And being a slow device, it takes it a while for the oscillations of that to stop. We never have such a signal in music. Nothing goes step from 0 to a max and stay there. And again, this is something that you can use if you're a designer and you're looking for some specific things. You know, maybe it has value. I've never commented on what this means or what it does. If you think you know what you want it for, go ahead, it's there for you to look at. But in general, everything you've seen in here is frequency domain. We care about frequency domain. Here in systems, a bank of auditory filters, and there's a filter bank in here. Very few things we do with timing versus what we do with frequency. So that's what the focus is there. So far, you're looking at the speaker like this, the measurements give you a picture. Measurements said, yeah, the on-axis response wasn't very flat. Wasn't bad, but wasn't flat. We had good bass extension, but we had some wobbliness in Twitter, in treble response. We had one resonance peak at 590 hertz, and I'll show you distortion. But how does it sound, right? What I do then is that I set up a speaker, in this case a near-field speaker, so I set it up in this near-field workstation. And if it's a normal domestic speaker, then I'll put it in my main system, which is way behind me, and then I listen to it. Now, I don't, while I have trained ears, I'm not doing this to tell you, whoa, I'll listen to it instantly, tell you how something a speaker sounds and rate it that way. That's a very difficult thing to do. I test about 100, 150 speakers a year. No way I could give you a 100% accurate assessment of every speaker based on, oh, I just heard it and there it is. Part of the reason is that audio is a broken architecture in that we don't know the tonality of anything that's produced. So if a speaker sounds bright, is it because of the music or is it because of the tonality? Now, I do have a set of tracks that I use for this purpose that I've calibrated to, but still everybody's fallible on this thing. So what I do is that I hook up the speaker, go through exactly the same set of tracks every time, and I form an opinion right away. I say, oh, that sounds a little bright, or that doesn't sound very good, or it sounds great. But fine, I'll put a pin in that, and then what I do is that I use my Roon player, which is what I use to play everything. It has a built-in parametric equalization, which means that I can design filters of different shapes and amplitude, and whether they go up or down, whether they pull things down, I can basically design any filter I want. And I start with the flat response, and then I go back to the on-axis response, and I say, okay, we saw this little peak in here. One, I design a rough filter. I don't try to design it mathematically where it looks exactly like this, but I say, all right, we're up 4 or 5 dB in here. One, I pulled out by, X amount of dB down and design a single filter. So I just designed this one filter over here, and you can see that's an inverse of what was wrong with the speaker. I'll plug it in here, and then with just that one filter in there, then I do an A/B test. Is it better before or thereafter? Depending on where the filter is, I play content that's sensitive to that. If it's a bass problem, then I play bass music. If it's higher up, then I use female vocals and other things. And I'll do an A/B test. And if needed, I do a blind test. Close my eye, randomly move this back and forth, and then I'll listen. Say this is A, this is B. Okay, which one's better? And then I open my eyes and take a look. Sometimes I can't decide, but many times I can. And when I think something sounds better with that same frequency response correction that the measurements showed, gives a very high confidence that there's that was needed, and what the measurements said in my room, in my situation with my music, was proving to be a good thing. The rest of it actually was tricky. You might think that you go and fill in those 2 dips. So again, we go up here. It looked like you should fill these dips to get them to sound better. I did that, and I thought it sounded too bright, so I went in inverse and pulled the peaks down in here rather than doing that. And once I did that and combined them all, I thought the speaker sounded really, really good. And this is not much of a filtering to apply to a speaker and to salvage basically what is an amazing value. You get a power 2-way speaker with 8-inch driver, it goes down to 39 hertz. And with just a little bit of filtering, it sounded near reference quality, and it beat, that's a majority of 2-way speakers I listen to. It plays powerfully and very cleanly, and so I was very impressed. Again, pulling this thing down actually helps with clarity and distortion that's pulled down. So as far as I'm concerned, my listening tests go hand in hand with measurements. They're not just an ad hoc subjective listen, oh, I listened to it and it sounded great and image this and that. No, my job is take the measurements as a compass and a GPS and say, all right, measurements said there were these errors in there. Can we improve if we reverse that problem? Now, certain things I can't fix. If the speaker's getting distorted playing low bass, is going to get distorted playing low bass. So there's nothing I can do about it. Yeah, I can filter that and see if it gets better, and sometimes I do that. But in general, the tonality issues I can fix. Okay, so very long presentation. Hopefully you stayed with me, but it's important stuff and it's complicated topic. This is something that on your own could take you 5 years to learn. Hopefully you got what you needed out of this. Maybe I'll do a follow-up video where I'll go through another speaker and give you more practice as far as how to read the measurements. Okay, thanks for staying with me. See you in a future video. Bye-bye.